In our Radial Buckley-Leverett problem, we want to talk about big and small terms. This is only possible if you have a dimensionless equation, so we need to pick some scales first. This is actually not that trivial. The correct scales depend on the problem you are studying. There's not one answer. In this video, you will learn how you can choose your characteristic length, your characteristic time and your characteristic velocity for your problem. Since this choice is not unique, I will keep those scales as unspecified constants in consecutive videos, so you can plug your own scales there for your own problems. So, what do we have? Well, you always, when choosing scales, you start with writing down your problem and your boundary conditions. So, we saw those two equations before, mass conservation of water and the sum of mass conservation of water and oil. Well, no matter what we are going to pick as R characteristic and T characteristic, that will be fine. This will always satisfy those equations, but then in dimensionless form. So if we want to see, well, what should we choose, maybe we can take a look at the boundary conditions. So what do we have? Suppose we are injecting water, then at our injection point our water saturation equals 1, and suppose we know what we are injecting, so how fast we are doing it. So suppose we have some Q inject, some injection volumetric flux. So how big is that? Well, what do you have? You have phi, a porosity factor, of course, times the flux, which is R times UW on the well, times factor of 2 pi times H. So suppose we know that, suppose it's given, so we open up a valve to some extent, so we know this quantity. And then, what do we have far away at R equals R reservoir? Well, we have some SW, probably it's cone water saturation. That's the final boundary condition. So, how are we then going to choose our scales? First of all, we'll use capital letters to denote dimensional variables and small letters to denote dimensionless variables. Now, take a look first at R equals RW, at this third condition. We have SW equals 1, so U water equals U total. So that means that we can here solve for R times U total. We see at R equals RW, R times U total equals this constant Q inject divided by 2 times pi times H times phi. Now, furthermore, we see that this R times U total does not depend on R due to equation 2. Now, it's constant for all times at RW. So at RW it's constant. At that time it's everywhere constant. And because this boundary condition is not changing in time, it's always constant. So this R times U total is constant for all R, for all T. So your volumetric flux, say if you make it dimensionless R times U total, which is RU total divided by the characteristic length and characteristic velocity, is some constant. So that's what we can use. So we can use this constant to get rid of one scale in terms of the other. Once we specify, for example, R characteristic, we can use this to compute U characteristic. But that leaves us with two options, because, well, U will be R over T, but it still leaves us with two scales. So we can either choose R characteristic and then fix T characteristic in terms of this flux, or do it the other way around. So what's the most convenient? That's up to you. So option 1, you can choose some characteristic length for your problem. So what should it be? Well, depends on your problem. If you are interested in phenomena which are very close to the well, it's best to choose R characteristic equal to RW. If you are interested in what happens in the entire reservoir, it's more, you'll probably choose your R characteristic to be R reservoir. So you will pick one of those. What you cannot do here is pick R characteristic R characteristic too small, like 10 minus 6 meters, because then you're not anymore on the Darcy scale, so that won't work. And picking R characteristic like 10 to the power 9 meters is also stupid, because, well, it would give you very small length. So you always pick something which is representative for your problem. Now, suppose you have some characteristic length in mind. Then you can use that to compute your U characteristic. Because what do? You want this dimensions RU total to be something like unity, like 1/2 or 2 or 1. Well, easiest is of course to make sure to pick your scale such that this RU total, the dimensionless version, becomes 1 with your scales. Because that means that if you're converting your equations to dimensionless form, that your boundary condition becomes 1. And then you can compare other terms with respect to 1. So what does this mean, this choice? Well, your RU total in dimensionless form is the dimensional one RU total divided by R characteristic times U characteristic. This quotient has to be equal to 1, so this quotient over here has to be equal to 1. So now you can solve for your U characteristic. Your characteristic velocity then will become R times U total in the dimensional form divided by your R characteristic. But you have something for R times U total in the dimensional form. It's given by your boundary condition over here. So you plugged it in over there. So there you have your U characteristic. And then you can, once you have your characteristic velocity, you can solve for your characteristic time, because your characteristic time equals R characteristic divided by U characteristic. So there it is. So once you have chosen some characteristic distance R, then you can compute your characteristic time T as follows. It's some combination of the physical constants. So that's option 1. So choose R characteristic, compute T characteristic and U characteristic using your boundary condition. Other option is to choose T characteristic and compute then your R characteristic. So you do a similar trick. You want again your RU total to be equal to 1, so you want this one to be equal to 1. So this quotient you want to be equal to 1 for some given T characteristic. Now you know U characteristic equals R characteristic over T characteristic, so that comes here. And then you can solve for your R characteristic. It's this expression over here. And again you plug in what you know about RU total. So that gives you your characteristic distance, and with your characteristic distance, your characteristic velocity. So that's the second option for you. So how do you choose your scales? As you see, there's not one way to do it, but you do it in such a way that your boundary conditions in the dimensionless form become nice. So that's what we did over here. RU total equals 1 in the dimensionless form. And you make sure that your scales really represent the problem you're looking at. That's what we did over here. You choose some characteristic distance which is really representative of the problem you're looking at. So here a lot of physics is coming in, and this can be different from problem to problem.